Hi, hello everyone. I'm Hung-Ming Lai from National Tsinghua University in Taiwan. And today I'm going to talk about our work on LoopDistribution for we are trying to improve the auto-vectorization in LLVM. So here's today's agenda. First, I will set up the background and motivation for the distribution and its current limitation in LLVM. And I will talk about how our proposed method implemented inside LLVM using the DDG, and also the scalar expansion we incorporated to enhance the partitioning capability. And then we will show our experimental results. So what is a loop distribution? It's a compiler transformation which will split a loop into multiple loops and with the same iteration space, but each loop will execute only parts of the original loop body. But it is not always profitable. So it's because it did not just reschedule the computation, it will also replicate some of the computations. For example, the loop header. So how does loop distribution can enable partial loop vectorization? So loops with dependent cycles is not vectorizable, and loop distribution will enable partial vectorization by splitting those cycles into a separate loops. And the current LLVM do have a LoopDistribute path, and its goal is also to enable partial loop vectorization. And its implementation is using a fast, lightweight algorithm and does not build dependence graph, and it relies only on loop access analysis. But this approach will have some challenge and limitation. It's based majorly in that it cannot reorder the memory operation. So it's currently now added in a path pipeline, but it's not enabled by default. So our focus of this work is that we want to try to improve its partitioning capability using the data dependence graph. And maybe in future we can have a better cost model for always profitable distribution. And here I want to go through 3 case studies for showing what's the limitation the current loop distribute paths face. So this one is taken from TSVC S221. And in this case, what we want to show is that before optimization by other passes like CSE and GVN, this code is distributable. It can be separated to one statement in one loop. But after the optimization, the redundant load is eliminated. Hence, the partition boundary is non-separable. And this is the second case, which we are showing this. There's 2 loops with identical computation, but only the order of the BI and BI-1 is shuffle, but only one pattern can be distributed. This is because the current loop distribute paths rely on the lexical order of the memory operations. And here's the third case, which is the dependent cycle caused only by final and the SSA value. So current loop distribute paths can detect the dependent cycle caused by memory operation, but not caused by the phi and SSA value. So it will not distribute this case, but this case is non-vectorizable. So the cause of this limitation is that it currently relies only on LAA, and this makes the reorder of memory operation unsafe. So it only distributes a certain pattern, which is the interdependent memory operation or placing the boundary formed by the unsafe memory operations. And it will also cause some merging if they are sharing the same memory operations. So there's many previous community efforts on these issues. Like in the first talk of this original author of the patch, they also mentioned the future work of adding dependent graph-based loop distribution. And all other talk also have mentioned the moving forward to using DDG-based distribution. And it's worth noting that currently the DDG patch is already on the LLVM upstream. But why is the DDG-based LoopDistribute is still not a reality currently? So we find the people mostly have concern with its scalability because to build a whole dependence graph, it will have a projected time complexity concern. So here's our plan in our work, this work. We want to try to integrate the available DDG analysis into the LoopDistribute path. And we try to cover all cases that is already handled by the current algorithm. And we will want to check the compile time regression by running some benchmarks. And for future work, we may, with this analysis, we can enable more cases and we can develop a better cost model for merging and scheduling. So here I want to quickly go through the classic textbook distribution algorithm based on dependence graph. So basically it has 3 steps. First one is we transform the source code to compute the dependence graph. So each node is a statement, and each edge is a memory dependence edge. Then we compute the LCC. So each LCC statement inside the same LCC should be placed in the same loop. And then the loop order it should be the same as the topological sorting order of the LCC dependence graph. So how do we adapt this algorithm into LLVM IR? The most trickiest part is the first part, because the original algorithm, one statement is mapped into one PDG node, but LLVM IR, we cannot place randomly one instruction into a different loop. We need to place all the independent instruction into the same loop. So we first look at how the current DDG graph looks like. So its node is using the instruction level. So it will have single instruction node or multiple instruction node, or the LCC in DDG, it will form a pi block. And their edge have only 2 kinds. One is the DU change, and the other is the memory dependent edge. It currently did not support control dependence, and its support scope have 2. One is function and one is loop. So you do not have to build all the dependence graph for the whole module. And so move back to the first step of the algorithm. So to adapt into LLVM IR, we just need to find the seed instruction, and we work up the DU change to get all the dependent instructions. But even with DDG, there are some cases it's not enabled by this method, because like the case study 1 we just mentioned, there will be low emulation that will mingle all the partition together. So we want to have a scalar expansion technique to solve this problem. So here's the motivation example. In this example, we want to separate the blue instruction and the green instructions. But these 2 seed instructions have depended on the same SSA value. So the intuition here is that we may want to reload the SSA value using a low instruction. And now that 2 will become separable. So this process is similar to scalar expansion optimization, and scalar expansion is typically used for breaking dependence, but it typically will involve new memory allocation. So for example, on the right-hand side, you will see that each iteration, it will assign to a new TI location, and it will break the cycle dependence created by scalar T. So what we want to do in the distribute path is that we want to detect the allocation-free expandable scalar, and the requirement here is that the store must write to a distinct address in each iteration, and the new load must dominate all the uses in other partition. So basically, it reverses the store load forwarding, and our heuristic here is that we just check the store pointer is scalar evolution computable, and we check it conform to the first requirement. And the second one is that we use the location of store to verify the dominance, because we currently insert the new load immediately after the store. So here's the recap of what we have done, and now I'll hand over for Yanrong for experiment results.
Hi, and now I'm going to talk about the experimental results. And our goal is to cover all cases handled by original LoopDistribute. And we'll mainly focus on the number of loops distributed. And we will also show the result of the compile time overhead. And here's the setup of our experiment. We will use the Intel Core CPU with LLVM 20 and compile the benchmark TSVC and spec CPU 2017. And in this trial, there are 3 configurations. And the first one is LLVM 20 without enable LoopDistribute. And the middle one is enable the original version LoopDistribute. And the last one is our DDG version LoopDistribute. And we can see that the numbers of loop distributed in most of the benchmark, our version had outperformed the original version, while there are still some cases had some regressions. And here we can see the number of loops vectorized. And remain half of the benchmark can outperform the original version, while the other half drops in vectorization. Then we will explain this result later. And here's the compile time regression. And all the compile times are in seconds. And we can see the rightmost column is about our DDG version compile time. And we can see that there's not a lot of changes considering of the compile time. And also in some benchmark, there show some reduction in compile time because in our DDG version, we are able to early exit when we found out there is no profitable loop distribution candidates. And also in this chart, we can see at the rightmost column is about the time that DDG analysis consumes. And we can find out that DDG only account for a small fraction of the total loop distribute path execution time. And as we can see now, our DDG version does not outperform across all benchmarks. So to explain this result, we will categorize the successful distribution into below 6 cases. And for the first one, in this kind of cases, it is able to be distributed by original version loop distribution. But we can see the partitions after distribution. All the instructions in partition 1 are contained in partition 0. So this kind of distribution is seen to be a redundant computation. So in our DDG version, we will eliminate this kind of cases to be distributed. And also the partition 1 will be possible to be vectorized. So this redundant distribution will also affect the numbers of loops vectorized. And here's the cases of runtime check. And in this kind of case, we have to add the restrict keyword to C and D. So we only have to consider about the A and B was not overlapped by others. While in the original loop distribution, it will ignore the alias age first and try to distribute the cases. While in our DDG version, we are unable to provide the runtime check feature because the DDG does not provide the alias information, so we are unable to handle this kind of case. And here's the case about the cases contains only dependency, which is a backward dependence. And this kind of case is unable to be distributed and also unable to be vectorized in the original version of loop distribution. But we can see the graph in the middle. This graph is the simplified DDG of the test case. So we can know that if we exchange the order of the statement, to put the second statement first, we are able to vectorize the sign of the test case without distribution. And this kind of case, we can look at the statement 2. This will be optimized to the phi instruction, while in the original version of loop distribution, we are unable to know this kind of memory dependency of the phi instruction. So in our DDG version, this kind of phi node will be inserted to the pi block and we'll see as a cyclic partition. So in our DDG version, we are able to distribute this kind of test case. And in this test case, we will assume that all the operands in the second statement will be loaded independently. So the left part is the original version. In the original version, this is able to be distributed. And also the right part is our DDG version. We are able to identify that the second segment is a cycle partition. And also it is able to be distributed by our DDG version. And the last cases is about what our works can do, but original version cannot. So we are able to use the scalar expansion technique to enhance the loop distribution. And also we are able to duplicate read-only load. And we can see this kind of test case, we have DI in both statement 1 and statement 2. But actually, in partition 0 and partition 1, they are identical low DI. So in the original version, it will be merged into one partition. So it will fail to distribute in the original version. Well, this is the same test case, but it's our DDG version. If we analyze there are multiple use on the load instruction, we will make sure that if this load instruction does not relate it to any memory dependency, we are able to duplicate this load, and so we can distribute this kind of loop. And here's the summary of supported cases of 2 different kind of version of distribution. And the upper chart is about the original version. The original version requires to preserve memory operation order. And our DDG version is the below chart. We are able to reorder the memory operations to enhance loop distribution. But the main limitation of our DDG version loop distribution is that we are unable to provide the runtime check feature. So this is because our DDG does not provide the alias information, so we are unable to do this. And also, we are unable to handle the backward dependence-only cases, because currently our method only deal with the cases with cycle. But if we can reorder the statement of the that I mentioned before, and we are able to vectorize this kind of case. So here's the reason why the half of the benchmark will show the drop in our DDG version. Let's first see the last benchmark first. And this because the original distribution has a redundant distribution. And this will also affect the numbers of loop vectorized. And about the other 3 benchmark is because our DDG version does not support with runtime check. So we are unable to match the performance with the original version distribution. And here's the end of our talk. Thanks for listening.
Thanks for your presentation. It's very insightful. And now it's the Q&A session. Anyone have questions?
The DDG was originally driven by IBM, who unfortunately shifted priorities, so that's why there's no use in LLVM for it now. So thank you making it useful. My question is for Spec 2006 Hammer, which was also the original motivation to even add a LoopDistribute pass in LLVM. So as far as I remember, LoopDistribute would split it into 2 parts, of which one could not be vectorized. And there was, I think, the control dependency in there, which would actually make it possible to split it in 3 parts. Did you check that's a Hammer benchmark and proof on that as well?
I think the Hammer benchmark is back to 2006. Yeah.
So this is later?
Yeah, we later...
You haven't tried it?
Yeah.
Or?
We haven't tried it on the 2007.
Thank you.
Yeah. Thank you.
Yeah, any other questions?
Hey, thanks for the talk. So you had this reload scheme where, you know, when you can figure out that a value can be reloaded, you put it in a new partition and break the partition. What do you? But that doesn't always work because the value might not be reloadable, and you don't want to introduce an entire array to hold intermediate values. But you can recompute the intermediate values. I mean, you basically can undo the merging by just, duplicating the computation. Have you looked at that?
Yeah, so we are planning to first version, and we can maybe model it in the future in the cost model, because we cannot currently like model how the recomputation costs in the original algorithm. So maybe after our add-in DDG, we can moving forward to like model how the different kind of code generation is better. Yeah.
What would you need to make like a what would help you to make a cost model and an evaluation? Like, what could one provide you to help you continue this work? Is there anything that is blocking you? Is there anything infrastructure you need?
Oh, currently maybe we still have no time to like work on this cost model, but our plan is like with DDG we can look at like the new partition including this area, or we just reload it and we can like try to compare the cost between these two versions. But it is impossible in the original LoopDistribute algorithm. So with DDG we can move on to work on.
Okay, to ask differently, do you have enough, like say, benchmarks or loops or little examples to actually validate all of this? I mean, do you need more loops or do you have enough?
I think we currently have some examples now. Okay. So
perfect. Yeah. Cool. Thank you.
Thank you.
Any other questions? If not, then let's thank them again for their great work.